So advanced deobfuscation, right? So one form of advanced deobfuscation that I want to touch on, right, or advanced obfuscation rather, is esoteric encodings. So we have familiarized ourselves with a few encodings. What encodings have we touched on? Base 64? Okay, Rod 13, yeah, I guess counts. Anything else? What's something that we keep looking at in like HXD and KJOI and everything? Hexadecimal. These are all encodings, right? They are all different ways of encoding the same data, right? But just in different representations. Now, this is something that is infinitely extensible, right? If you have any format that carries some form of information, it can be a way to encode information, right? For example, what if you had an image file, right? And then every single pixel of the image file actually encodes the data that you're trying to transmit. Better yet, what if you hide the data encoding inside the image? For those of you that might have done forensics before, you might be familiar with the term steganography, right? This is a form of hiding data inside other images or other files using unique encodings. So for example, the most common form of esoteric encoding for image stego is called MSB or LSB. So it uses the most significant or least significant bit of a pixel value and uses that to hide data. So this sounds like it's very abstract, right? But this is something that's actively being used by malware. So one example that I'm going to raise, let me see if I can find it, right? Let me just Google malware payload and image. So there's a few articles here, right? And this is something that has become very popular within, I'd say, the last 5 years, right? Where people are hiding malware inside images. So you can see like all these little like patterns, right? That is an encoding of data inside the image. And if I'm not mistaken, the North Koreans did use this recently. Let me see. North Korea. Not this, not this. Okay, this one they're hiding it inside SVGs. SVGs are vector art files, so it's encoding data in vector art, right? I do want specifically image. ISO image, okay, wrong, right? Not the thing I'm looking for. Yeah. Let's see if I can pull up this article. So you can see in this chain, right? Let's see, is this correct as well? I do need to look. Blah 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 blah. Weaponized image or HTML via Dropbox. So it hides its payloads in image files, and then it uploads it to Dropbox, and then it pulls it from Dropbox, and then it decodes the image into the malicious code that it wants to run, and then it attacks your computer, right? So a reason why they want to do this is because it is stealthier, right? When we are looking at base 64 or hex, it's damn easy to tell it's base 64 or hex. At this point, after 2 days of workshop, okay, while waiting for this to come back, it hit the timeout. After these 2 days of workshop, right, you should be able to identify base 64 just by looking at it, honestly, right? So obviously, if a piece of malware also uses base 64, then it's very simple. You just look at every base 64 string, then you just whack it, then you see what it is, right? So they need to use more creative methods. When they are using images, encoding data inside images, you have to remember that people use images all the time. When you send images on Discord, send images on Telegram, send images over email, it's not treated as a suspicious action most of the time, right? But in this case, the malware is able to use the image to transmit data, able to transmit additional payloads. So what we're going to look at is a much more advanced and much more complicated malware sample. Well, not exactly a malware sample, but just a dummy program which uses a very unique form of encoding to hide its payload. So if you want to follow along, you can. Although this part, I won't blame you if you get lost. Right? Don't save. So there's a few learning points I also want to bring up along the way that hopefully some of the information won't stick. Sorry, will stick, because I didn't put it in the slides. So it will just be based off my narration. Okay, what we're going to be looking at is under day 2 materials, decompilation IP address. Hopefully that gives you a clue as to what sort of encoding we're looking at, right? And there should be a file called IP, like to rip IP, like IP address, right? So let's just analyze this. So the thing is, when you run this for analysis, right, it will take a lot longer to perform analysis than usual. And if you notice, the file size for this program is really big. It is 1.14 megabytes, which is quite unusual. Because if you go back to our rat from earlier, right, this whole malware sample, which was able to download files, gut processors, fingerprint your computer, perform encrypted communications, everything, was only 46 kilobytes large. But somehow, this other program is over 1 megabyte large. That's a massive difference. That's over 20 times in size, right? Better yet, okay, so I'm going to run the program because this isn't dangerous, right? I'm going to run it just so you guys can see what we expect the output to be. If you run it, you just see the flag, flag number 1 yippee come out, right? But if you go to define strings, obviously, and then you search for it, you're not going to find it anywhere, right? So some sort of data obfuscation is being used to prevent us from finding the flag. Okay, sure. So what we're going to do now is, once analysis is done, I'm going to show you guys some really special attributes about this program, right? Which makes it quite different from the stuff that we've been looking at so far. At least something that I want you guys to notice first, while analysis is still going on, it's still ongoing, right? Notice anything weird about the function name? What's odd about it being main.main compared to everything we've been looking at so far? Dot something, right? Usually we just look at main, but suddenly we're looking at main.main. Then it got main.invoke, main.generate, right? This isn't the calling convention that we're used to, right? We've been seeing just main, generate, invoke. Now suddenly it's main.something. Then somehow if I go into the functions, you'll see main.pass. The decompilation is also really ugly. You can see here and there, like Gidra keeps saying subroutine does not return, subroutine does not return, right? It's not as nice as the things we've been looking at so far. Another thing, does anyone remember where the compiler would put information about what compiler was being used? There's a specific section. Anyone remember? Easy name. Okay, it's a defined string, but it's a defined string in what section? What section would the compiler information be put in? Comment, correct. This is the first string in our defined strings list. That's in the .comment section. So this is the comment telling us what compiler is being used. Just now, every program that we look at, the compiler has been called GCC, right? But now for the first time, we're seeing a compiler called LLD. So it's a different compiler. And on top of that, there's a GitHub link there, and you can see it's to a GitHub page called Ziglang. And if you search out what Ziglang is, right, you'll find this is the Zig programming language. So Zig is a different programming language from C, and it has a different compiler. So different source code, different compiler, and different compilers will produce different compilation output. So this, even though we're still looking at an L file, right? Our L file structurally is fundamentally different because it came from a different programming language, was processed by a different compiler, and as such, the structure of the program is very, very different. So what do I mean? Well, here's one structural change that we can observe. Try and open the imports folder on program tree. is blank. This program does not import any libraries at all, right? And this is something that even the Linux system knows. If you try to run file on it, so remember file gives you some information about the file. I want you to notice these few lines. Statically linked, not stripped. So if we compare this to something else that we were looking at earlier, right? So if we look at like elf3, if we look at elf3, which if you recall is me when I'm turtle, right? Notice how it says dynamically linked versus statically linked. Anyone have any guesses what the difference between dynamic and static linking is? Yes, correct. So the difference between dynamic linking and static linking is that in a dynamically linked binary, right? Remember the analogy that I used to compare it to Python is when you're importing, like import libc or import libcrypto, it's like writing import time, import math, whatever at the top of your Python script, right? And every time you do that, you can just use the code from those modules directly inside your Python script straight away, correct? You don't have to go to the time module, copy the entire script, paste it into your one to use its functions. We agree with that? So that is called dynamic linking. It's dynamic because it is done dynamically, right? It's importing from somewhere else. This is compared to a statically linked program. So statically linked programs do not import external libraries, or they minimize it to the absolute bare minimum, right? For the most part, everything that it does is self-contained. So that means instead of import libcrypto, every single crypto function that it needs will be inside the binary. Instead of import libc, any standard function it needs will be imported inside the binary. And you can see how this very quickly makes the binary very, very fat, right? Because imagine every single library that you need, every single function from every single library now has to be packaged inside the same program, just so your program can run. Now this may seem disadvantageous, right? Because, hey, if I can just import it and then it makes my file size 20 times smaller, why don't I just do that? Can anyone think of a very obvious benefit of using static linking? They don't have the library, right? So, I mean, we saw this issue just now. A lot of y'all didn't have scapy installed. Then I tell you import scapy, right? Then cannot. If I statically link my Python script, then you guys wouldn't have had to pip install scapy. You would have just been able to run the script and it would have just worked. Similarly, if I have a statically linked program, I could have it do all sorts of really advanced functionality and have it not have to rely on you having a specific library installed on your computer. So, how is this beneficial? If I am a software developer, right? One advantage of having a statically linked binary is that now I can send my file to anyone and I don't need to worry about them having to download .NET runtime or having to download some external library or whatever. It will just run on their computer. This is a design decision that was made for the programming language Golang, right? So Golang, right? Golang, which is a language designed by Google, is a statically linked language. So every binary that you compile with Golang, confirm plus chop is statically linked. But this means that if you write Golang on Windows, you can compile the binary for Mac and for Linux and for Windows at the same time. Because it's all statically linked. It's all using the same code that will shove into the same binary. So it's very, very reliable, right? And then Google doesn't have to ask people to import XYZ, import ABC. They just drop the binary there and it works. This is very useful for malware as well. Because imagine, like, let's say your malware needs to perform cryptographic functions, and somehow, by stroke of God, right, your Linux distribution does not have OpenSSL on it. Then all the crypto functions we saw earlier won't work, right? It can't do encrypted comms anymore. So what if you just put every cryptographic function that you need inside your program? And there you go, now it can run on any one system. This is where the joke hella gangweed ChatGPT Golang ransomware comes from. Yeah, that's not a reference they're gonna get. But it's why Golang is also a very popular target for analysis in industry, because there's so much malware that's written in Golang nowadays because of this statically linked attribute. right? The fact that it runs on so many systems without issues, without dependencies. Okay, so zig. In this case, we have a statically compiled zig binary. Before we start going into the weeds of it, I will also now drop you with another tidbit of information. This one lost the class a bit yesterday, but we have a bit of time, so I'm going to try and explain it, shell coding. So we have this function called main.invoke, and the structure of this function is very weird, right? We see the following operations being done. We see mmap. Anyone can guess what mmap stands for? If you can't guess it, you can Google it. Memory map. So it maps memory, which means it allocates some memory, right? So there's some memory being allocated here. Then we see our good friend. What's our good friend over here? Memory copy. So it copies some memory into this allocated buffer. Then this. Huh? Anyone know what this syntax is trying to represent? This looks like a function call, right?
Associate a variable to a value.
Nope.
You're associating a variable with something, I guess.
Yeah. This one very esoteric. Well, not very esoteric, but it's a bit outside of anything that you've seen so far, or anything that you have seen in Python, for that matter.
Is it related to pointers?
It is semi-related to pointers, right? Because this, I guess you could think of it as it's pointing to some memory, right? And that it's, but how is it treating the memory? So, I want you guys to look at the disassembly for a moment, because it might elucidate a tiny bit. Notice that the disassembly here, what instruction is this? No. In green. Call.
Get right.
What? No, but call, right? What does the call? What does the what does the assembly instruction call think? Like, what do you think it does?
Just gets a value.
Nope.
No.
Let me-
Run a function.
Let's scroll up a tiny bit. The last time we saw call being used was on call memcopy, and then it decompiled to running the function memcopy. So call RAX means it is running the memory as a function. So this is a very foreign concept to you guys, I believe, right? But this ties in with our layers of abstraction. Remember, at the very lowest level of abstraction, all programs are just bytes, correct? They're just machine code, they're just bytes. Our programs, our ELF files, give those bytes structure so that the operating system knows, hey, what section is our machine code in again? Usually in an ELF file. Dog that memory. .text, right? So you tell a computer, oh, I got ELF file here. Then the computer like, interesting. Then it's like, oh, my machine code is in .text. But in the .text section, all of this machine code is just bytes, right? So what if instead of doing all of that finagling and putting the bytes in places and whatever, what if I just put the byte somewhere, then I tell the computer, hey, I got bytes over here, treat it as code. Then the computer will look at it and like, oh, right, that is machine code. This is a concept called shell coding, which is also very, very commonly used by malware, and actually something that you see a lot in binary exploitation. So over here, what it describes, shell code, a small piece of machine code that's used as a payload, right? It is raw bytes that when you hand over to a computer, and then you point the computer at it and be like, hey, call these bytes as a function, it will be able to run those bytes as a function. So this is actually quite cool, right? Let me pull up a payload. For example, on Linux, right? If you have a program and you pass in these 23 bytes into a, like you put these 23 bytes in an array, and then you call the array as if it's a function. So you call the array like this, right? The CPU will just start reading these bytes as if they are regular assembly instructions. And once you run this, it will open up a shell. Like it will drop you into binsh. So this is called shell coding, and it's a very old concept actually. It's all the way back from the 90s when people first started doing binary exploitation, and then people realized that you could leverage it for malware as well. So why am I bringing up shell code? Well, it's because this program execute shellcode lah, right? If not, why I bring it up? So in some way, our program is going to take some bytes that are encoded somewhere inside it, and then it's going to run it as shellcode. And then when it runs it as shellcode, it will perform some action in this case, right? In this case, we know that the action that it will perform when it runs the shellcode is it will print out the flag for us somehow. So let's start digging into the binary to see where the shellcode could be. Now this one is really I want to get your gears turning, right? Let's go to main.generate. So in main.generate, if you scroll down, okay, again, like I'm gonna go a bit fast because you don't necessarily need to follow along for this one. I just want you guys to see the content and try and digest it. We got a while loop. I'm gonna rename local 18 to I because I know it's a index counter. We can see a very familiar pattern. We are taking two arrays, indexing them character by character, and we're performing XOR on them. What's this? XOR encryption, right? XOR encryption or XOR decryption. So we have some data that is XOR encrypted somewhere inside the program, and that is a form of obfuscation, right? And we're going to decrypt it later. So local 460 is some array 1, and local 230 is some array 2, so like something like this. And then finally, it will be written to some output. Hey, cool, right? Now, with our powers of analysis and using our eyes, we can see that XOR array 1 is being used as a parameter inside the function main.pass here. See, there's some function called main.pass, and it takes in XOR array 1, and it takes on XOR array 2, right? So those values are probably getting filled out by main.pass. Another thing, what global variables can we see here? Just read them out. Globals. anon 23833 and anon 23841, right? Weird sounding global variables. If I double click on them, and then I look at them inside the bytes view, do these look like anything to y'all?
IP addresses.
Look like IP addresses, right? So that's interesting. How come this global variable and this global variable, both of them seem to be filled with IP addresses? Okay. I'm going to just rename this into, I don't know, IP array 1. And I'm going to call this one IP array 2. Okay, then let's quickly take a look at main.pass. What's inside main.pass? In main.pass, that lines up with our assumptions. It makes a call to the function pass IP. So this is where I want to get your gears turning when it comes to encodings, right? So we're familiar with IP addresses, yes? Something dot something dot something dot something. 0.0.0.0. Is this a valid IP address? Yes or no?
Yes.
Yes, right? 1111. Valid or not? Yes. 192.168.13.2. Valid. 300.123.456.789. Valid or not?
No.
Not valid. Why? 255 is the maximum value that each slot can hold. So 255, 255, 255, 255 is the maximum value of an IP address. Agreed? So that means that each IP address range is 0 to 255, 0 to 255, 0 to 255, 0 to 255. Agree? What else has a range of 0 to 255 that we have seen? Hexadecimal. 0x00 to 0xFF. That's also 0 to 255, correct? Agree? So what if we did the following? What if I have an IP address ABCD, then I just convert it into bytes ABCD? You see how this works? Like 192.168.13.2. If I turn that into 192.168.13.2, then I can turn this into bytes 192 is 0x. I don't know. I pull up Python. Hex of 192. 0x C0168 is, oops, A8. Then 13 is 0x 0 C D E F E D. I'm so good at this. Then 0x02, right? So you see, our long IP address 192.168.13.2 can be represented as 4 bytes, right? It can actually be equivalently represented as C0 A8 0D02. You see where this is going? So inside our program, our gigantic IP address arrays are secretly encoding bytes. It's just we have turned the bytes into a different encoding, which is IP addresses. So I wrote this script yesterday on the spot. So now it's already been written for you all to look at. Yippee, right? Where is IP address? So I wrote a script yesterday which takes all those IP addresses that we can see. So these are the bytes of the IP addresses from the program. Then it just splits it up, and then it decodes it, right? Because there's a library in Python called sockets, right? So if I import sockets, I don't have sockets. Oh, import socket, my bad. So if I have an IP address, I can do socket.inet aton and then like 192.168.13.2. Wait, 192.168.13.2. And then you see, I get C0A801, and actually I should print this as hex so that you can see it clearer. C0A80120. Okay, it's because I did 1.32, not 13.2, so it's different from what we were talking about just now. There, C0A8 0D02. That is what we managed to calculate by hand earlier. So I would take all the IP addresses inside the binary, I will extract them out, I'll convert them from IP addresses into bytes, then I will XOR all of the bytes together. And then I will just see what this gives me. So you see, after running it, the decompilation output isn't going to be something readable per se. Well, the XOR output isn't something going to be readable per se because this is machine code. But we can see fragments of the flag in here in plain text. You see, I.YCEP, 8 only, 1, ag number, right? So fragments of the flag are visible in plain text because what this shellcode is doing is it's taking these fragments and rearranging them to give us our flag, actually. But yeah, so this is an esoteric form of encoding, right? We have taken data and turned it into something that's a bit more familiar in some senses, IP addresses, but less familiar to us as analysts, right? There's some other really obvious encodings that you can use. For example, I don't know the syntax for this.
.uuid.
Yeah. UUIDs. So these are like unique ID identifiers. You can see they're just hex strings, right? So imagine a binary that's filled with strings of UUIDs, but actually each UUID is secretly encoding some shellcode or some secret payload that you want to run. Okay, so that was the detour that I wanted to take with regards to esoteric encodings, right? Hopefully that was informative in some sense. If you weren't able to follow along the whole analysis, it's okay. My main takeaway that I want you guys to have is that there are different ways to encode data besides what we've seen, base 64, hexadecimal, now IP addresses, right? There are many unique ways that encodings can be done, and super advanced malware will come up with all sorts of really creative ways to hide their data. I'm not gonna go through this because it's a lot more complicated. Okay, so that is more or less the bulk of the main content for this workshop, right? As a TLDR, right, as a recap of what we've learned from day one, we learned about files, Okay, well, we learn about what malware is precisely first, the different types of malware. Then we learn about files, we learn about hex dumps, we learn about file magics, file structures, file signatures, right? We did some forensics, right? So we learn about program files, app data, the registry, um, caches, right? Then we looked at decompilation, whereby we looked at analyzing ELF files in Ghidra, right? We looked at some networking, we understood some network protocols, extracting information, decrypting information, so on and so forth. So these are all aspects that are relevant in the industry when it comes to malware analysis and reverse engineering at a professional level, right? And these are the first few tools that you have to pick up in your tool set if you want to do this at a more professional capacity. So some things that you can do to gain more experience or more knowledge about malware or reverse engineering at your own time, right? There's this website, malwareunicorn.org, right? It has two reverse engineering courses, right? With a particular focus on 32-bit Windows binaries. Now, it's very weird because nowadays Windows is all 64-bit, but because of backwards compatibility, you can still run 32-bit on Windows 64. And a lot of malware is written in 32-bit for some reason, right? So it breaks down P32s in particular, right? And instead of using Ghidra, it uses a more advanced air quotes, depends on who you ask, right? Decompilation software called IDA, the interactive disassembler, right? And it teaches you how to do dynamic analysis with X32 debug. There is class.malware.re. This is, I'll send the slides. So don't worry, right? This is the malware analysis and reverse engineering course from the University of Cincinnati, right? Where it teaches their students from whatever baseline knowledge they have how to do static analysis with Ghidra, how to do debugging with this debugger called Immunity, right? It teaches them about Yara rules, which is something that we didn't really touch on in this course, but it's similar to how Detected Easy is able to identify programs so easily, right? Oh, it's Detected Easy because it's easy to detect. Huh. Anyways, yeah. No, so Detected Easy uses this thing called signatures, right? Yara rules are just even more complicated and more advanced signatures to help us identify specific strains of malware really quickly, right? It also touches on some types of malware that I simply had no time to cover in this course, which includes PDF malware, Word document malware, Java malware, Android malware, right? If you guys like reading books or don't mind reading books, practical malware analysis, this is the golden standard for learning reverse engineering through a structured textbook per se, right? It uses IDA, it uses Oli debug, and it has some really advanced malware that it analyzes. So it even looks at kernel level malware that sits below the operating system as you know it, right? And it covers a lot of the anti-analysis that malware uses as well. If you want to do practice challenges for reverse engineering that are more CTF-like, so something that's more like just find a flag, reverse engineer the algorithm type of thing, crackmes.one is a good resource. I know some of you all might have tried like Pico CTF or something like that before. Pico does have decent reverse engineering challenges, but they're not great, right? Crackmes has definitely more quantity than quality, but the few good crackmes are really good, right? So I do recommend that if you want to try and gain more experience with reverse engineering in Ghidra, for example, right, with smaller examples, smaller programs to look at, crackmes is a very good place to get started, right? Just do the really high soft rate ones.
Yeah, just do mine.
Okay, and that's it. That's all my slides. You guys can ask questions or anything more to do with this. I don't have much more to add in terms of main content.